Hello and welcome to today's webinar. Today's webinar, we're going to be discussing obtaining the best solar yield with Fronius inverters. Today will be myself, Byron Kutzer. I'm the Technical Sales Advisor for the Southern African region. And joining me today is David Nwangi, who is the Technical Sales Advisor for the Eastern African region. So for today's agenda, we'll be covering PV panel optimization, maximum power point tracking, dynamic peak manager, and lastly, our active cooling. Before we start, please feel free to ask questions during the webinar, and we will attend to your questions as soon as possible by one of my colleagues. Lastly, your opinion is very important to us, so we would appreciate if you can please give us feedback regarding the webinar. So what factors affect your solar yield? So there's 8 most important factors that affect it. Your geographic location, time of day, period of the year, your atmospheric conditions, as well as your PV panel layout, panel orientation, temperature, and lastly, your DC cabling. So on the PV panel layout, you've got a series layout. So this is a best practice where all modules in series should be the same type of module from the same manufacturer, as well as never mix panels with different short circuit currents in series. So this allows for more flexibility, so you can mix panels with different voltages when they are strung in series. And the performance of the solar array is as strong as the performance of the weakest element, with important note. So this is just a demonstration on the PV panel layout. So here, for example, we've got 3 400-watt solar modules with a 40-volt VOC and a 10-amp current rating. So this is where the total voltage open circuit is 40 plus 40 plus 40 is 120 volt, and the total current is 10 amps spread by the 3 panels. So this gives us a total power of 120 volt times by the 10 amps. So this is 120 watts, which equals to 3 times by the 400-watt modules. The second example is where you are using a 200-watt module, which has got only a 200-volt rating, but it still has the same 10-amp rating. So this will again give you an open circuit voltage of 100 volts. Again, the total current is 10 amps. So this is then therefore 100 volt by 10 amp, which is then 1 kilowatt, which equates to 200 watts plus your 2 by 400 watt modules. An important note is if you are using a less watt module as well as the voltage is the same, but the current is different. The current is what will affect your system itself. So in this example, it will be the same. So it's the 120 volt open circuit. And then your total current is obviously derated by your lesser module itself. So the 200 watt has only got a 5 amp rating. This means there will be a 120 by 5 amps, which gives you a total of 600 watts, which that equates to, it has derated those 2 remaining modules of 400 watts down to 200 watts each. So the total current is determined by the panel of the lowest current rating when in series, which is important to make note of. The next we'll be talking about a panel layout which is in parallel. So the best practice again is all modules in parallel should be again of the same type of module and from the same manufacturer. Never mix panels with different open circuit voltages in parallel. And again, you're more flexibility, so you can mix panels with different currents in parallel. Whereas with series, it's the other way around. So you can never mix panels with different currents in series, and with parallel, it's with different open circuit voltage. So here, for example, we've got again 3 modules, so it's 400 watts. So your total voltage is 40 volt. So it's 10 amps plus 10 amps plus 10 amps. So it gives us a total of 30 amps is available. So this therefore means that your total power is then 40 volts by 30 amps, which equates to 1,200 watts, which again is 400, 400, 400. Whereas, for example, if you have a 200 watt module mixed with a 400 and 400 watt, so again, your voltages will be the same, but the current is different on the 200 watt. So here we have an example of your 40 volts is the total voltage, and your total current is then your 5 amp plus 10 amp module plus another 10 amp module, which gives us a total of 25 amps available on that string. This will then be the total power, so it's 40 volts times by the 25 amps, because we've added all them together, which gives us a total of 1,000 watts. An important thing to make note of to avoid is by using different voltages. So again, this is an example of what will happen. So here we're using again a 200 watt module, but it's got a 20 volt rating instead of a 40, where the rest of the modules in the string are 40 volt with 10 amp. So this will then, therefore, our total voltage is only 20 volts, but our current again is 30 amps because 10, 10, and 10. So this will therefore mean our total power is again 20 volt by 30 amp, which is then 600 watts. So what it effectively means is that we have derated these 400 watt modules down to the current rating or voltage rating of the 200 watt module in the series, in the string. So again, the total voltage is determined by the panel of the lowest voltage rating when in parallel. So PV, and further on PV panel layout. So the number of PV modules in series is calculated by using the following equation. So this is the total number. So this will be your voltage of DC max. So it's your voltage open circuit times by 1 plus your extreme temperature coefficient that you are using. So let's say we are using 70 degrees centigrade as an example. So it'll be 70 minus 25, close brackets, times by the temperature coefficient that we have, the temperature coefficient of open circuit voltage of the PV module, which is a percentage degree in centigrade. For PV panel orientation, so the general rule is that the PV system in the northern hemisphere should have panels facing true south, and the PV system in the southern hemisphere should have their panels facing true geographical north. So for the southern hemisphere, if more energy is used in the morning, then the panels should face northeast. If more energy is used in the afternoons, then the panel should face a northwest orientation. So the angle of a solar panel should be set to produce the most energy in a given year is determined by the geographical latitude. So the general rule for optimal solar energy production is to set the solar panel tilt angle equal to the geographical latitude. So for example, we're using Lagos in Nigeria, so its coordinates is 6.5 degrees north and 3.3 degrees east. So this means that the latitude is therefore plus minus 7 degrees. So hence the tilt angle for the panels should be 7 degrees due south. So the temperature effect. So what effect of temperature on the PV cells itself? So when the temperature increases, then the current SC of the panel increases, and this is a proportional relationship. When the temperature increases, the VOC, so this is the voltage open circuit, of the panel decreases, and this is inversely proportional relationship with regards to the voltage. The temperature has a greater effect on the voltage than it has on the current itself on the modules. So for example, what would be the current and the voltage open circuit and the power of the module on a 395 watt panel? So here we know that the current is at 25 degrees centigrade, which is the normal testing conditions, is 10.82 amps, whereas the voltage open circuit at 25 degrees is 47 volt, and the power max of the module at 25 degrees centigrade is 395 watts. So here we're using a current temperature coefficient of 0.05% degrees centigrade, and then the voltage coefficient is minus 0.28% per degree centigrade, and then the power coefficient is then negative 0.36% degrees centigrade. So what is it at 50 degrees centigrade? So we will then use the data that's provided by the module manufacturer, which is normally located on the back or on the data sheets. So here we can see is the normal power rating, optimal voltage, as well as the open circuit operating current, as well as the open circuit voltage and the short circuit current that's then labeled on the module itself. So here if we wanted to calculate the current when it is at 50 degrees centigrade, so here we know at 25 degrees centigrade the current is 10.82 amps. So here we will then multiply that plus the coefficient that we have for the current at 25 at 0.05% per degree centigrade. So that will be then the temperature that we're wanting to monitor minus the standardized testing temperature, which is 25, divided by the 100. So that means that at 50 degrees centigrade, this module will then be outputting a current of 10.96 amps. On the next section on DC cabling. So DC cabling sizes. So the current carrying capability must be equal to or greater than the current to be carried. A good suggestion is to always size for 1.25 times the normal current of the system, as well as to must be able to withstand environmental conditions, so to be exposed to open elements. And special attention needs to be paid to the voltage drop with increasing of the cable length. And then consideration has to be placed on whether the cable is standard or solid core. Next is the specific conductance of the cable has to also be considered. So this is the normal conductance of copper, for example, per meter, and then aluminium. Next is the maximum power point tracking. So inverter product parameters. So here we can see that what does the inverter data say about its capabilities. So here we know that the maximum number of MPPT trackers is 1, and the max input current for IDC max is 47.7 amps, and the max short circuit current per module array is 71.6 amps. So that means that per every array we can have a maximum of 71.6 amps. And then also for the DC input voltage range, so this is the input voltage range that of the inverter can handle. So this is from 580 to 1000 volts. And the feed-in start voltage. So you have to ensure that your PV strings voltage is above said 650 volts with the Eco 27 in order to then start PV production. Whereas, for example, on a Cyma 10, which has 2 MPPTs, so then we'll have 2 different input current ratings. So we'll have a 27 or a 16.5 amp. So this allows us to have 2 different inputs having 2 different currents. So we'll have a 40.5 amp and 24.8 amp. Again, the DC input voltage range, the UDC min and UDC max. So this is from 200 to 1000 volts. So again, your feed-in start voltage is 200 volts. So you need to ensure that your module string is above 200 volts in order to enable the inverter to start producing and feeding in power onto your grid. So next is your PV production parameters. So the module current is directly proportional to your irradiance. Low irradiance means low current. High irradiance means high current. So only minimum changes in the voltage at different irradiance values. So the irradiance is only going to greatly affect your current itself and not the voltage of the module, whereas the voltage of the module is greatly affected by temperature. Next is, what is your main causes of yield losses? This can be design related, common setup and configuration mistakes, not following recommended procedures, cable sizing for instance, as well as loose connections, your irradiance variations. So if you've got high irradiance variations, it will greatly affect your yield, as well as the effect of the module orientation. So if you've got a southern hemisphere project that's being installed, but most of your modules are south orientating, that will greatly affect the yield of the plant itself, as well as shading, and as long as also is considered is your lifetime degradation. So your modules will degrade over time, so they will lose a certain amount of percentage of efficiency over the next coming years from the manufacturer. So what happens when the input DC voltage is not optimal? So this is for an example of all Fronius snap inverters except for the Eco series. So the Eco series has a narrow high voltage range. So to maintain efficiency, the booster current is switched on or off, and it depends on the input voltage. So if the voltage is below 300 to 595, the booster is on, and then from 595 to 800 volts, the booster is off. So that is why it's always typical to scale your PV between 595 to 800 volts. Next is the Superflex design from Fronius. So some inverters have a main and secondary input. So this is if the two MPPTs exist. So one takes 80% of your PV array and the next will take 20%. So this is why you have different current ratings. So for example, on the SIMO 10, it was 40.5 and 24.8. So this will allow you for much greater PV array on your MPPT1 compared to MPPT2. So other inverters are designed with equal inputs. So that means that your MPPT1 takes 50% and your MPPT2 takes 50%. So none of the MPPTs can carry more than 50% of your total PV array. Whereas with Fronius Superflex design, combines the two variations into one design. So this gives you a higher point on tracker A or on tracker B. So this means you can do an unsymmetric distribution, for example, with shadings of 80% and 20%, or you can do a symmetric distribution, for example, in east-west orientation, we are using 75% and 75%, basically oversizing. So what does the Superflex design address? So it addresses different orientations as well as unsymmetric PV installation spaces. So it allows you to orientate on one, so this is for different orientations, as well as your unsymmetric PV installation. So you can have much greater input on PV1, for example, or PV2, and then have another separate strings on MPPT2. So your typical commercial roof spaces. So in most cases, the modules will be installed facing one direction, typically north or the southern hemisphere, for example. 2 or 3 orientations also possible depending on the roof complexity and location. A combination of Fronius inverters can handle even the most complex roofs. For example, a combination of a SIMO and Eco. So this is where you'll have 2 MPPTs on the SIMO, and you'll have the Eco only, managing 1 MPPT. Whereas our new Fronius Taro 50 kilowatt standard, which has got 3 MPPTs, and this presents another flexibility level. So it's having one inverter that has 3 MPPTs with a 50 kilowatt size power class. So how many MPPTs are therefore ideal in an inverter for design flexibility? So next I'll be handing over to my colleague David, who will be continuing.
Thank you, Byron, for the first part of the presentation. So I will now be taking over and take you through the remaining bit of it, and starting with the dynamic peak manager. So the dynamic peak manager, as far as Fronius inverters are concerned, is a technology that is embedded as standard in all Fronius inverters. And in addition to the normal MPPT algorithm, the dynamic peak manager is assisting the inverter to basically look at the best operating point as far as maximum power is concerned. So therefore, this allows faster adoption to changing irradiation levels. And the algorithm will scan the IV curve every 5 minutes. And every time a new MPP is fouled, it will compare it with a previous MPP to check which one has more power before shifting to a better operating point. So this dynamic peak manager feature can actually be accessed through the basic menu section of the Fronius inverter. And if you desire to switch it off, you can do that. But the default switch setting when it comes from the factory is on. So for example, if you have a system that you're installing with DC optimizers, then you might require to switch off the dynamic peak manager. So this is one of the use cases of accessing the dynamic peak manager through the service menu. So just to conclude or to sum it up is the fact that the dynamic peak manager is a highly efficient shadow tolerant algorithm for Fronius inverters. So therefore, let's look at how you can maximize your yield even at a shade or at a shaded conditions. So we have talked about, also my colleague has talked about maximum power point tracking, and within the Fronius inverters, whether it's a single MPPT or two MPPTs inbuilt, you have the normal scanning of the maximum power point. So, and this is done to maximize extraction of power from the PV array at all conditions. And therefore, for this to happen, then you have to scan the IV curve. So looking at the best operating point. So, however, there are some problems with typical or normal maximum power point tracking algorithms, because in the case of shading, then the tracker often stays at the local maximum power point without finding the new global maximum power points. As you can see on this graph to the left, we have 3 curves. So one at midday, so the blue one without any shade, and then you have another one at 9 in the morning with a bit of shading, and also one in around 8 a.m. with also a bit of shading. So for the one that are shaded, then we have 2 possible operating points. So we have what we refer here as the local maximum power point and the global maximum power point. So if this MPPT is not able to adjust or adapt the operating parameters, then it will often stay at the local maximum power point when the array is shaded. So this therefore means that you have reduced yields because the tracker remains kind of stuck at this operating point. So just to give you a practical example, what this would mean, we have a 3.3 kilowatt peak system. The orientation is southwest and with a tilt angle of 19.5 degrees. And as we can see from this illustration here, we have a bit of shading. So almost half of this array is shaded. So what would the effect be therefore of this shading? So this shading is happening from around 8:45 in the morning to about 10 a.m. And the daily yield without the DPM is as per this graph, as we can see it. So therefore, it means we are losing this part of the shaded section of the graph where the array is shaded from 9:45 to around 10 a.m. So Fronius offers a solution within every of our inverters with a dynamic peak manager as mentioned. And therefore, instead of the inverter staying at the local maximum power point, the Fronius inverter is able to intelligently shift the operating point. And this happens by either increasing or reducing the operating voltage. So as you can see on this scale, if you are starting from 200 volts, the inverter is able to shift the operating voltage upwards to find the global maximum power point. Or if at the point of shading, the inverter was at this point, local maximum power point, then it can also shift the operating voltage downwards to find this better operating point. So what this means is that you have more flexibility as far as your installations are concerned, and therefore you do not have to worry too much about things like a nearby chimney that would shade your array for part of the morning, because the dynamic peak manager is able to address this kind of challenges. However, please note that you should try as much as possible to install your PV array where there is no shading. But in the case that it's totally unavoidable, then you have a huge advantage with the Fronius Dynamic Peak Manager. So the question therefore is, how much then can this Dynamic Peak Manager guarantee? So the area graph that we looked at, the yield was lost between 8:45 and 10 a.m. But with the Dynamic Peak Manager, we have this yield, the area shaded now in green, that you can be guaranteed even when your array is shaded. So to put it into perspective, the Dynamic Peak Manager from Fronius can give you 7% more yield. And just to take an example, if you have a 300 kilowatt peak system that is operating 6 hours per day, as an example, this 7% means that you can produce an additional 126 kilowatt hours per day compared to an inverter that does not have a dynamic peak manager. So extrapolating further and say, assuming that you are going to operate for about 9.5 months per year, it means with a dynamic peak manager, you are able to guarantee additional yield of at least 36,000 kilowatt hours. And over the life of the system, which in this case we've taken about 20 years, you can guarantee about 718,000 kilowatt hours. So if your cost of power then is about $20 cents, over the life of the system, you can save or earn in the case that you are exporting power to the grid. But if you're not exporting power to the grid, then it means that you would have saved about $143,640. So you can see that the Dynamic Peak Manager has a huge impact on the savings that you can get from your PV installation. And therefore, we can say by conclusion that the bigger the system, the more the savings. And therefore, Fronius guarantees with this integrated Dynamic Peak Manager that you're able to get a lot more yield from your system. One of the other things that would allow you to get extra yield from your PV system is active cooling. So, and what is the concept of active cooling, and why is it better, a better technology for power electronics? So by definition, we can look at this as a technology that is proactively put there to avoid hotspots from developing within an electronic device. So the fans are then used to remove warm air from the inverter in a controlled manner. And also for all Fronius inverters, active cooling is a standard technology, or is a standard feature. So therefore, in addition to a heatsink, there is a fan to ensure that the air inside the inverter is circulated and therefore avoids creation of hotspots. And then an external fan ensures that the heatsink stays at a low temperature, as low as possible. So we have now the variation between the typical Gen24s and the snap inverters. So you can see the cooling concept of the snap inverters. The fans are taking cold air from the sides, and hot air is coming out from the top. But you can see also a big variation here with a better design of the cooling concept of the Gen24s, where you have a centrally placed fan and a heatsink that is covering the entire front side of the inverter that is able to dissipate the hot air out of the inverter. So one of the things that has to be avoided within an electronic device, such as an inverter, is the creation of hotspots. So what is there for the effect of active cooling on these hotspots. So when you have active cooling, so like you said, for the snap inverters, similar concept also for the Gen24s. The only difference is the number of fans. So you would have normally one fan for cooling the heatsink and another one internally within the inverter to make sure that air inside the inverter is circulated. And this prevents the creation of hotspots. So you can see from this illustration, we have about 13.4 degrees Celsius within the Fronius inverter that has an internal fan in addition to the heatsink cooling that is actively cooled. But when it comes to a passively cooled device, so it relies on convection cooling and you have no external fan, but some of these passively cooled inverters could still have fans inside the inverter for air circulation, but still you can see that the temperature at one spot is quite high. So it's at 23.6 degrees Celsius. And therefore this can easily lead to creation of hotspots within the inverter. So the first one would be the ideal case when the temperature is kept as low as possible for the electronics inside. But the next one is not so ideal because easily this can create some kind of thermal runaway within the inverter if it's not checked. So going further, let's look at the advantages of active cooling. So active cooling has quite a number of advantages. So you can be guaranteed of less costs. This means that as far as things like OPEX are concerned, you have less maintenance to be done on the inverters. Cleaning as one of the routines that has to be carried out on passively cooled inverters. With actively cooled inverters, the cleaning does not have to happen as frequently. You are guaranteed more yield, so the inverter is able to perform better. So it's able to therefore guarantee you with this safe cooling technology that you have better return on investment. You have ease of installation, and this comes from the point of view that actively cooled inverters do not use very big heat sinks, and therefore the weight of the inverter is not as much. You have a lot of flexibility in terms of mounting the inverter. So as you're going to see a few slides later, the Fronius inverters with active cooling are very flexible in terms of how you can position them for mounting. And the icing on the cake really is that with active cooling, you can guarantee that you have the longest lifespan out of an electronic component. And for a PV inverter, this is one of the things that you have to look out for, that we have designed a system for 20-25 years. Is the inverter that you're using that is really the most vital component within the setup going to last as long as the design life of your system. So when it comes to mounting and the flexibility you get out of active cooling, so with active cooling, basically we have no limitations. And here we are talking about the allowable mounting positions from Fronius. So you can mount the Fronius inverters from 0 degrees up to 90 degrees. So you can see a vertical installation, maybe a variation between vertical, which is 90 degrees to 45, and then from 45 to about 0 degrees, which is a horizontal installations. In most cases, passively cooled inverters would only be mounted at this position, which is vertical 90 degrees, because then if you do any other variation, convection cooling does not happen as efficiently. But with active cooling, this really is not a limiting factor at all. So with active cooling, we have said also that you get a longer lifespan of the inverter, and the conclusion from a lot of studies is that the hotter power electronics get, the shorter the lifespan. So if you increase, for instance, the operating temperature of an electronic device by just about 10 degrees Celsius, then you essentially cut the life of this device by half. So, and therefore active cooling guarantees that you have less stress on the electronic components, and therefore you can have optimal or let's say desired service life out of that particular gadget. So, and this equation basically explains this fact that for every 10 degrees increase, then the life of this gadget is cut by almost half. So you have more yield with the active cooling as well. So if an inverter is exposed to high temperatures, the output power will be derated. And this is one of the ways that electronic components, especially inverters, will try to protect the electronics inside. So, but inverters with active cooling have better power derating behavior because the cooling effect is stronger than when you're talking about passive cooled inverters. So in this graph, we can see a comparison between a Fronius actively cooled inverter and a passively cooled competitor. So, and we can consider different input voltages because also the input voltage, depending on the ambient temperature or the operating temperature, is a factor also to consider. But generally, you can see that for a Fronius inverter, going up to 850 volts, let's say a Fronius Echo, you would have the rating at just about starting 45 degrees Celsius, but a competitor at 800 volts, 30 degrees Celsius ambient temperature. So this is a huge difference because then this gap between the two lines, the blue one and the red one, would mean that this is potential yield out of your PV system that you could use. So if you do expect that your ambient temperatures are going to be, let's say, above 30 or 35 degrees Celsius, so you can experience this kind of temperatures, it's actually always good to go with an actively cooled device because then your yield is guaranteed. So if we analyze further the impact of power derating due to temperature, so we can see here a graph of production, and this is a system that is about 99.84 kilowatt peak. So it gives out 90 kilowatt AC power, and this is a system in Australia. So by looking at this graph, the conclusion is that if this system was done with a passively cooled inverter instead of actively cooled inverters, the yield loss would have been significantly 15%, the section that you can see here, because this is a production with an actively cooled inverter. But if then we were to do a passively cooled inverter, then you can see around midday and up to 3 p.m. thereabout when the production would be highest, and the ambient temperatures are also quite high, then a passively cooled inverter would derate the power output from your inverter, meaning that you're not getting the most of your PV system. So with active cooling, we've also said you have cut on your maintenance costs. So also for your end customers, this is a benefit that they would be able to enjoy. So therefore, if you used a passively cooled device, they have some recommendation on the routine maintenance that has to be done. So one of these things that has to be done is system cleaning that has to be done every 6 months. So, and here you have to check that, for instance, the heatsink is free from any dust or blockage. The procedure here is that you have to turn DC power off, then on at night at some point to clean the oxides of the DC switches, for instance. But with an actively cooled inverter, the fins or the heatsink fins are naturally cleaned by the air that is being pushed out of the inverter by the fan. So therefore, you can see that for a passively cooled device, you're going to have higher maintenance costs, particularly in dusty regions or locations. So there are also some myths and claims about Fronius active cooling. So we can look at one of them. So what happens, for instance, to devices with fans as far as the IP protection or the ingress protection rating is concerned? So the claim from some quarters is that Fronius inverters cannot achieve IP66 if their inverter has a fan. However, in reality, the fact is that fans are actually sealed internally and have a rating of IP67, which means that this fan can actually operate even temporarily underwater. And therefore, you can see that the fans would have a higher IP rating than the Fronius inverter, so to speak. So the fan is IP67 and the inverter is at IP66. So, and the construction of the cooling mechanism, the fan is not pushing air inside the inverter, as we have mentioned before. So it's just blowing air over the heatsink. Then internally in the inverter, there's another enclosed fan that is circulating the air to prevent the creation or the formation of hotspots. There is also another debate about if you have a fan in an inverter, what is the expected lifespan of this fan? How often do you need then to change or to think about changing the fan? So to give light to this debate, there were some studies that were done a while back, And out of those studies, 2 devices exposed to extreme high temperatures were studied over a period of 1 year. And the hours of the fan operation were categorized into 5 ambient temperature categories. So in steps of 10 degrees. So as we can see, we have from 20 to 30 degrees, 30 to 40, 50 to 40 to 50 degrees, and then 50 to 60, and then the very extreme of 60 to 70 degrees Celsius. So these were systems in Italy, as we can see the color codes here, the UK and Australia. So in terms of how often these systems operate under these conditions, so you can see that in the UK, for instance, you have a high number of systems that would operate between 20 to 30 degrees. And in Australia, you'd have quite a number of systems that would operate between 40 to 50 degrees, as we can see here. So from this, we can conclude that, as we can see, that the design of the speed-controlled fans in the Fronius active cooling concept is such that the fan only runs at full speed if the ambient temperatures exceed or reach 60 degrees. So we are talking about very extreme cases here. And as we can see here, only very few portion of the systems were operating above 50 degrees. So as we can see, majority of them were operating from around 20 to 50 degrees ambient temperature. So therefore, this means that in practice, the operation of the fan would only occur at full speed, because this is what now determine what is the life of the fan, in very, very few cases, meaning that the cooling fan would have a service life of more than 20 years. So in hot areas, in addition, I think this was a point that was mentioned by my colleague earlier, is that if you look at the irradiation curve, you can see that there is an effect on voltage as a result of high temperatures. So in areas where modules are exposed to high temperatures, then the output power from the modules is less, meaning that the inverters are also not operating at full power, means that the fans in most cases would run a lot less hours, meaning that we can easily exceed this 20-year expectation from the manufacturers. So that brings us to the end of our webinar today. But before we end, I would like to give you some further details. So as an installer, where can you get additional information about Fronius products? You can do this easily on your own from the Fronius website. Just remember that we have 3 business units. So you go to the Fronius website, fronius.com, then you click on business units. Then you'd have to go to the solar energy business unit. And from there, you can then go to the installers section. So there you can find homeowners, business owners, but the most relevant for installers is the installers and partners. And then from there, you have an array of information that relates to different categories. So products and solutions, you have their technical data, you have info center, you have service and support, and then downloads as well as contacts. So this is information that you can easily get on your own at any time, anywhere. So in terms of also recordings, if you would like to look at one of the webinars or the trainings that you have done before online, you can go to the YouTube channel. There is a dedicated playlist for the Sub-Saharan Africa region. So there you enter this link, and you will be able to access all the webinars that you have done in the past. If you'd like to contact any one of us, if you are in West Africa, please contact Cyprian Okolo. In Southern Africa, please contact Byron Kotze. And in my region, East Africa, you are free to contact me. So here is our contact details. If you'd like to contact Fronius directly from the head office for any concerns, these are the contact details as well. So we are always very happy to talk to you regarding any issues that you might have. So, and with that, we've come to the end of our webinar today. Thank you very much for joining today. And we do hope that you have enjoyed the webinar and have gotten a lot of useful information. And we do look forward to seeing you in the next topic to be covered in 2 weeks. So for now, thank you and goodbye.